Good afternoon, class. So this is going to be our first asynchronous lecture, unfortunately, because my kids need to be picked up from school right in the middle of lecture. So what that means is that I'm going to record this and you can watch it during normal lecture time. And if any questions come up, feel free to ask me, or you can watch it. You know, if you're doing this asynchronously already, you can watch it at your own pace. I will try to be available also during lecture time if you're wanting to watch this, and we'll have my Zoom open for you to hop on with any questions. As a reminder, your topic is due today, by the end of the day, so get me that, what you're wanting to use for your research project. And with that, let's hop into this, and hopefully it works smoothly. So where is, I get to the slide deck here. Find the slide deck to get to the slide deck. Here we go. So for today, we're going to be talking about colligative properties. Colligative. So to ligate is to bring two things together. So we're talking about bringing things together for today, and how that relates to certain things like boiling point, freezing point, the role of osmotic pressure on those things, and so forth. So start off by saying that the changes in these colligative properties that we'll talk about that are below depend on the number of solute particles present. Remember, we talked about solutions on Tuesday. Solute is what is going into the solvent to form the solution. So the colligative properties depend on the solute particles present, not necessarily the identity of the solute particles. Okay, so we're going to be talking about how solute and solvent relates to their amounts, the moles of them. And that is going to shape certain properties like lowering the vapor pressure of a solution, the boiling point, the melting point, and what's called the osmotic pressure. Now, because a solution is made possible by the intermolecular forces between the solute and the solvent, if we have higher concentrations of non-volatile solutes, it's going to be harder for the solvent to escape into the vapor phase. Okay. Now we're talking about non-volatile, meaning we're talking about the properties of things that don't readily evaporate. Okay. So things like acetone would be volatile, or chloroform is an example of a volatile chemical. Ether, these things evaporate quite readily. So assuming it's not something like that, the higher the concentration, the harder it is for the solvent to escape into the vapor phase. Okay, keep that in mind. Now, there are several units that we use to express concentrations of solutions. Molarity is a big one, and that's going to be the moles of solute over liters of the solution. Okay, so the total liters of the solution. Okay, and this is helpful when we are doing stoichiometry. You probably dealt with molarity to some degree in Chem 101. And it's defined in terms of the molar amounts of a particular solute, okay? So moles solute over liters of solution. However, solution volume can change with temperature, right? It can expand or it can contract. And so likewise, molar concentrations can vary. So when we're talking about molarity, the concentration of that solution, which is going to have, say, the same amount of solute and solvent, would be different if you change the temperature, right? Because again, the volume is contracting and expanding, okay? So to get around that, we use other units such as molality or mole fraction. Molality tends to be more appropriate in this case, okay, when we're talking about colligative properties, because they're mole-based. It doesn't matter what the temperature is, okay? So in this case, molality is the moles of solute over the kilograms of solvent. So different from molarity, which is moles of solute over liters of the solution, because of that, because the solution can change, we just say moles of solute over a certain amount, in this case, kilograms of the solvent. And then also the other expression is mole fraction. So that's going to be designated as X. It's the ratio of the molar amounts, okay, of, in this case, the solute, so the moles of solute over the total moles of everything going into that solution. So the moles of the solute and solvent. So this is a mole fraction is just moles over moles. And with that, we can then calculate the mole percentage or the mole percent, okay? Another way of looking at this is that the mole fraction, or X, is equal to the amount of solute in moles over the total amount of solute and solvent in moles. So N solute over N solute plus N solvent, okay? And then when we take that number, we multiply it by 100%, we get our percent mole. And then here's a table that just breaks down these different terms for you, so you can compare them. Molarity, molality, mole fraction, mole percent. That's what we've talked about, right? And then you can do parts by mass, which is mass of the solute over the mass of the solution. We can look at percent by mass, and then we have like ppm, ppb, parts per million, parts per billion. That's a very common calculation when talking about concentrations of certain things in a solution. Oftentimes when we talk about toxicity, what is the ppm or the ppb that is acceptable in our drinking water per se? Like, so if we wanted to say we're using atrazine as a pesticide, and some of that's gonna eventually leach into the water system, what is the parts per million or the parts per billion that's an acceptable dose in our drinking water? Here's another way to look at these things. So we can express concentration as moles or liters or kilograms. And depending on what's on the numerator and what's on the denominator is going to give us our term. Okay, so if we're looking at, for instance, moles on the numerator and liters on the denominator, that gives us molarity, right? If we're looking at, instead of moles, kilograms, that is density, right? Because what's density typically? Grams per milliliter. So if we just multiply that by 1,000, we get kilograms per liter, and so on and so forth. So if we said, what is the concentration of 29.2 grams of O2 in 5.0 liters of water in mole fraction? Remember, what's mole fraction? The moles of the solute, so the O2, over the total amount of solute and solvent. So to solve this problem, you would just have to convert 29.2 grams of O2 into the respective moles, right? So you use your conversion factor with the molecular weight to convert that, and that will give you moles of O2. And then you will take that over the sum of those moles of O2 and the moles of water. Well, how do we find the moles of water? Again, we can take 5.0 liters and convert that into grams, and then take that by the molecular weight to get moles and add those two together, right? So it would end up looking like, try to text, it would be the moles of O2 divided by the moles of O2 plus the moles of H2O. Okay, that would give us our mole fraction. And then moles per kilogram, what's that? That's molality, right? So again, we already have our moles that we've figured out for 29.2 grams. We just convert liters to kilograms. And we would have converted the liters to grams initially to get our moles. So we just convert those grams to kilograms, and that gives us our molality. I'm not going to go through this because I feel like this is fairly straightforward and stuff that we've done. If you guys have questions on this, feel free to ask Arina or Sean or me during our respective office hours and tutor times. But in the interest of time, I want to just chug along forward with some of the more involved stuff. Okay, so what volume in milliliters of a soft drink that is 10.5% sucrose by mass contains 78.5 grams of sucrose? So what is the volume if it's 10.5% sucrose and has a mass of 78.5 grams? And they tell us the density of the solution is 1.04 grams per mil. So how would we figure that out? Well, for this, what we can do is we can very simply just designate a certain amount to get our percentage, okay? So we're saying it's 10.5% sucrose, and we want to essentially get that into a non-percent form. So we could say that let's just assume that we have 100 grams of the solution. So if we have 100 grams of the solution, and we put that over 10.5 grams of the sucrose, that will get us, or I'm sorry, we flip that, right? We take 10.5 grams over 100 grams. That's essentially the ratio that we're getting when we're taking it out of the percent, okay? That will give us a number. And then we have 1 mil. We said the density, right, is 1 mil for every 1.04 grams. That's what 1.04 grams per mil is, right? So with that in mind, we just set up some conversion factors to get to the total answer. And I'm going to pause it here And what I encourage you guys to do is to pause it yourself and see if you can work this out. And then I'm going to write some stuff on the board, and then we'll do it together. Okay. All right. Okay. So we're given that it's 78.5 grams of sucrose at 10.5%. All right. So we want to get rid of that percent. And again, 10.5% is just going to be 10.5 grams out of 100 grams solution in theory, right? That would give us that 10.5%. So if we write it with solution on top, grams on bottom, then we can get rid of that percent and get it as a ratio, all right? And so the answer is asking for it in milliliters though. And if they give us a density of 1.04 grams per mil, that means, again, as a conversion factor, 1.04 grams equals 1 mil of that solution, okay? So we put our mils on top and 1.04 on bottom. And what that should do is that should cancel out our grams, right? And give us a final answer in mils. And if we do that, we get 78.5, 100 divided by 10.5 divided by 1.04. I've got basically 719 mils of that solution. Okay. So very simple, straightforward way to calculate different aspects of a solution, whether they want it the mils, or they want the molarity, or they want the molality, or they want the percent. Knowing all of these different values, we can just set it up with the conversion factors to get what they're asking for. So here's some additional practice. A solution is prepared by dissolving 17.2 grams of ethylene glycol in 0.5 kilograms of water. The final volume of that solution is 515 mils. For this solution, calculate the concentration in each unit. Okay, so what we're going to do is they're going to say calculate this in terms of molarity, molality, percent by mass, mole fraction, and mole percent. So I'm going to pause it. I want you to work on this, and then we'll go over it together. But remember to use these tables in the previous couple slides to help you out, to tell you what molarity is, to tell you what molality is, and mole percent, etc. Okay, and if this one works better, then you use this one. So use those tables, and then see how you can express 17.2 grams of ethylene glycol in 0.5 kilograms of water in these different terms.
Okay, so I've written it out as A, B, and C, and then I ran out of board space. So we'll do those first three for starters. They're asking for the molarity to start with. And we know that molarity is equal to the moles of solute over the volume of the solution. And in this case, we're given the grams of ethylene glycol. So we got to convert that into moles. To do that, we have our conversion factor, right, using the molecular weight. So we have 17.2 grams of ethylene glycol times 1 mole over its molecular weight, which you add this all up, you get 67.07 or somewhere around that. And that is going to now give you moles, 0.277 moles. So that's our moles of solute. Then we just take the moles of solute and put it over the volume of the solution. And they said that the volume of the solution was 515 mils. So to make that liters, we just move the decimal point over 3 times. We get 0.515. And that gives us an answer of 0.538 molar. If we wanted to express this information in molality, remember that's going to be the moles of solute over the kilograms of solvent. Okay, we already have our moles of solute because we calculated it for A. So we take 0.277 moles over 0.500 kilograms of H2O, which was another piece of information in that problem. And we get 0.554 for our molality. And then for C, percent by mass is going to be the mass of the solute over the mass of the solution, and then multiply by 100 to get our percent. And so our mass they gave us was 17.2 grams. The mass of the solution is going to be the mass of the solute and the solvent combined. So the solute was 17.2 again, plus 5.00 times 10 to the 2 grams, because remember they gave us kilograms. And so we want it in grams just so that the units are all the same. And then you multiply by 100%, you get 3.33%. Okay. And what are the other things they're asking for? Let me go to the slide deck. They want mole fraction and mole percent. Okay. So remember that our mole fraction is the moles of solute over the moles of solute plus the moles of solvent. So let's get that going. And that's going to be similar to our molality, right? So for D, mole fraction, or X, right, we say that's the moles of solute over the moles of solute plus the moles of solvent. Okay. So we got to get moles of our water. Again, that was, what was that? 5.00 times 10 to the 2 grams of H2O. And then our conversion factor, 1 mole of H2O over the molecular weight, which is 18.02. If you want to be precise, or just 18 will work. Grams of H2O. That will give us moles of our solvent. We already know that the moles of the solute was, I erased it. 0.2771, I think. 0.2771. moles. 0.277, something like that. We'll go with it, okay? I trust my instincts. So it's going to be this over 0.277 moles plus 18.02. No, sorry, I'm getting ahead of myself. I got to do the moles of that first. So let's get the calculator out. If I do 5.00 times 10 to the second divided by 18.02, I get 27.75 for this. This equals 27.75. 27.75 moles. Okay, so that's going to be this time plus 27.75. Now, let's do that. Let's do 0.277 divided by 0.277 plus 27.75. And I'm getting 9.88 times 10 to the negative 3. 8 times 10 to the negative 3. Okay. So moles of solute over moles of solute plus moles of solvent. And then what was the last one? Mole percent. Okay. So E mole percent is just going to be the mole fraction of the solute times 100%. So 9.88 times to the negative 3 times 100 is 0.988% for this. Okay. So we just took this number times 100%. So all different ways to express the same relationship, right? I mean, we were given the same amount, the same information to do all 5 of those different representations of that information. Pretty cool. Okay, now I think in the interest of time, I'll skip over this, but it's asking for the molarity of a 6.56% by mass glucose solution. And they give you the density. So this is going to be very much like what we've already done in, what was that? In the previous problem. When we were looking at 10.5% sucrose, set it up basically the same way. Okay, so I think I'll let you guys work on that one. But essentially, you're going to take the 6.56% and put it into grams and set it over 100 grams, right? Arbitrarily, just because it's 6.56%. And then we multiply it by our conversion factors, right? 1 mole over the molecular weight of sucrose, or of glucose, sorry, in this case. And then the density is
1 milliliter equals 1.03 grams. And so they should all cancel out. And from there, you can determine the molarity, because remember what's molarity? Molarity is going to be, well, maybe I'll go over this one because it has that extra step of molarity. So pause it here, see if you can actually do this on your own, and then we'll meet back up and go over it. And I'll write a little bit on the board to save some time, okay? Oh, shoot. Well, I think I might have made a mistake. I think I forgot to start recording because it just said recording in progress. Ouch. So you'd think this would be my first time, but I did this all for Chem 103 last quarter. I don't remember if I went over this problem or not. So I'm not going to go over it a second time, but this is what it is. I'll let you guys snapshot it. This was the problem looking at the molarity. And so to do that, we took theoretical 6.56 grams of glucose over a theoretical 100 grams of solution up here, and calculated the moles if that was the case of glucose. And then if our solution's 100 grams, we figured out what the liters would be at that given density. And then we took moles over liters to give us our molarity, okay? And then there were a couple other problems that I said I was going to skip over in the interest of time. If you want to work on those problems, they're again, similar kind of things, solving for molality or molarity or mole fraction. If you want to work on those in the slide deck, by all means, please do. Practice makes permanent. And if you want any help with those, come see me during my office hours, or you can talk to Erina or Sean, okay? And then I got into Raoult's law, which I don't think that we covered. So I'm going to backtrack and give that spiel again and hopefully not make that mistake again. Okay. So where? All right. So I said Raoult's law talks about partial pressure of an ideal solution. And we can say that the partial pressure of an ideal solution is equal to the mole fraction of some component times its vapor pressure, okay? So we're talking about component A. So whatever part of that solute that's going into solution or solvent that's making up the solution, we can determine the pressure by taking PA and setting it equal to the mole fraction of A times the normal vapor pressure at a specific given temperature. And then I also said that assuming the substance is non-volatile, meaning it doesn't spontaneously evaporate or evaporate very quickly, and the solute is non-volatile, we can express Raoult's law as the vapor pressure of an ideal solution is equal to the mole fraction of the solvent times the vapor pressure of that solvent. Okay, and we can say that because the vapor pressure is essentially negligible because that solute isn't evaporating and contributing to any gas hovering over the solution. It's just going to be made up of the vapor pressure of the solution itself. And then I said, let's work on this problem. So it wants to know the vapor pressure of the ideal solution. So that first P, when they give us 92.1 grams of glycerin, they give us the formula, and then 184.4 grams of ethanol, they give us the formula. So that's the solution. We're mixing ethanol and glycerin together, and we're keeping it at a constant temperature of 40 degrees Celsius. And the vapor pressure of pure ethanol is 0.178 atmospheres. Glycerin is essentially non-volatile. Okay, so we can use that P solution equals P solvent times P, or
times mole fraction solvent. So you got to find the mole fraction, which we worked on just previously, and then use that to multiply by the vapor pressure, and that will give you the vapor pressure of the ideal solution. Okay. So now I'm going to pause it. I'm going to have you guys pause it, and then we'll go over it. Try to work on it on your own though. Okay, so they've given us a solution containing 92.1 grams of glycerin and 184.4 grams of ethanol. And they said it's at 40 degrees. They said the vapor pressure of ethanol is I didn't write it down, but 0.178 atmospheres. Glycerin is non-volatile, so that's not going to be contributing to the vapor pressure. And they want to know what is the vapor pressure of the ideal solution. And so we got to do, right, P equals mole fraction times P, right? So we got to find mole fraction, right? We have P, the vapor pressure at 0.178 atmospheres. We're solving for the P of the ideal solution, so all we really need is the mole fraction. We're given grams, so we multiply by our conversion factor, the molecular weight of glycerin being 92.094. That'll give us moles of glycerin. To get moles of ethanol, we multiply it by its conversion factor, 46.069 grams. It's the weight of ethanol. That'll give us moles of ethanol. And then our mole fraction, remember, it's the moles of our ethanol versus the moles of the two components of the solution total, the sum of those. This over the sum of this, okay? So let's compute that, shall we? Let's take, this is going to be, pretty close to 1. In fact, I think we just call this 1. Just to be simplified, 1 mole of glycerin. Remember, the grams cancel, right? Okay, and then 184.4, whoops, 184.4 divided by 46 point, gives me 4, I like it when it does this, 4.00 moles of ETOH, or ethanol. So it's just going to be, 1 mole, well, let's get our sig figs, 1.00 moles of ETOH over 1.00 moles of ETOH plus 4.00 moles of glycerin, essentially 1 divided by 5. I'm sorry. This is 4, that should be 4. Yeah, 4 moles. 4 divided by 5, right? That's going to give us, for this, it's going to give us a mole fraction. This divided by this is 0.8 times 0.178. So times 0.178. That gives me a 0.142 atmospheres of our ideal solution. Okay? Get out of your way so you can see that. So the big part of this calculation was just doing the mole fraction. And to get to the mole fraction, we just took grams, good old stoichiometry, grams to moles. Okay.
here's another problem that, again, you guys can work on to calculate the vapor pressure at 25 C of a solution. Needs 99.5 grams of sucrose and 300.0 mils of water. Vapor pressure of pure water at the same temperature, 25 C, is 28.3, and assume the density is 1.00 grams per mil. Okay, so that density is just given to say we can convert directly from mils to grams for the water. Okay, so practice this. It's the same thing. You need to convert to moles, find the mole fraction. They give you the vapor pressure at 23.8 torr, and then you got to find the overall vapor pressure of the ideal solution. I won't go over this, but if you would like to go over this later, again, come see me during office hours. Because I want to get into the next colligative property, and that's going to be boiling point, elevation, freezing point, depression. So raising the boiling point of a substance by putting it in solution, lowering the freezing point of a substance by making it a solution. And we are all very familiar with freezing point depression if we live in Tahoe or other places where it snows, because they put salt on the road. The salt forms a solution with the water, lowering the freezing point. So that means it's going to have to be a lower temperature for that solid to remain a solid. And so then it melts. And this should make sense, right? For freezing point depression and boiling point depression, assuming that, again, these are non-volatile interactions, or interactions between non-volatile components. Because when you complicate something, when you add things together, you're changing the intermolecular forces, right? A solution is outcompeting the intermolecular forces of the solute and those of the solvent and creating new attractions, okay? So remember, what dictates a freezing point and a boiling point? Their degree of intermolecular forces. And so if you're changing those, you're going to change their properties, okay? And that's why adding salt to water changes its freezing point. And we can calculate all this by using this equation. We can say that the change in boiling point is proportional to the moles over the kilograms of solvent in the solution, okay? So the change in TB, that's the boiling point, temperature of boiling, is equal to I. I is Van Hoff factor, which we will talk about. It's not really going to play a big role in the first couple problems, so we'll talk about it later on. We can simplify it and just say that the change in boiling point temperatures is proportional or equal to K times molality, right? Because molality is moles over kilograms, okay? And K is going to be some specific constant that is relative to a particular solvent, okay? And so the constants are different if you have different solvents. Benzene has a constant of 5.12, chloroform 4.70, water 1.86, so on and so forth, okay? But if we know two of these three, or if we have other information that we can use to then calculate molality, we can determine how that affects the boiling point. And so let's try it. We have a mass of ethylene glycol, which we've done before, in grams. What mass of ethylene glycol must be added to a 1.0 kilogram of water to produce a solution that boils at 105 point C, okay? So again, remember this lower equation. We don't have to concern ourselves with Van Hoff's factor just yet. Just focus on the change in temperature in TB equals KB times molality. See if you can come up with this. And I will pause it. And this time, remember to unpause it and we'll go over it together. Let's see what you can come up with on your own. Okay. So as we said, change in boiling point is equal to this constant of the substance times the molality. We're asked for the mass, okay? It doesn't give us the mass, but we can get to the mass by finding the molality because they give us the change in temperature. We can look up the constant, the K, find the molality. And then once we find the molality, we can convert that back into mass, okay? So I'm gonna backtrack. The change, it said, was for, remember, it says the solution now of water boils at 105, right? So our delta T is 105.0 minus what it normally boils at, our temperature initial, 100. So that's going to be 5.0 degrees Celsius is our delta T. And if you look back at that chart, I think I was pointing out the KF constants when I was talking about this as examples. So you disregard that. Actually, over here to the right is the KB constants. So when we get into freezing point depression, then we'll talk about these. But if we look at water, it's 0.512. Okay. So we just say that we can rearrange this equation to get molality by itself and say molality is equal to change in temperature over the constant. And so that's 5.0 over 0.512. If we divide that out, we get 5 divided by 0.512. I get 9.77 as our molality, okay? So if that's our molality, what else are we given in this problem? We're given 1.0 kilograms of water. Okay, so that's good to know. So let's take, let's start up here. Let's take 1.0 kilograms of H2O. And what can we do with that number? Well, we can say that the molality, right? What is molality? It's our kilograms and the relationship of moles and kilograms, okay? So if we have 1.0 kilograms, we can multiply that by a conversion factor of our molality, 9.77 over 1 kilogram of H2O, okay? Because it's this moles, right? Or molality is 9.77 moles over 1 kilogram of that substance, in this case, water. And so that will give us, then we can times that by the molecular weight. And so that molecular weight is, again, we're looking at ethylene glycol. So if we look up the molecular weight, .07 grams of ethylene glycol, C2H6O2 per 1 mole. Okay. Essentially, this is now a mole. If we're expressing the molality, we can say molality equals moles over kilograms. So we can say that this is moles.
And so now it cancels out. Our kilograms of H2 are oh, wait a minute. Oh yeah, kilograms. Kilograms of H2O are moles, and now we just get grams. And that's what they're asking for. So if we compute all that out, essentially it's just 9.77 times 62.07. I get 6.1 times 10 to the 2 grams of C2H6O2. Oh, gotta get my exponent in there. There we go. Okay. So that's the mass of ethylene glycol that we would need to raise the temperature. Now, interestingly, ethylene glycol is what's an antifreeze that you put in your car to keep it from freezing and busting your engine and the pipes and stuff. Because it does this. It raises the temperature of, well, I guess, yes. I mean, well, we'll get into that when we talk about freezing point depression. But if it's raising the boiling point, chances are it might also raise the temperature required to freeze the water. Okay. So that's that one. Here's another problem that you guys can work at on your own, dealing with boiling point elevation. And again, we can go through these during office hours if we want some extra help. Okay. So that brings us to freezing point depression. And it's going to be similarly expressed, only it's instead of TB and KB, it's TF, KF. It's going to have slightly different, or really radically different constant values. Okay. But we apply it in the same way. But this will get us to now, I want to talk about Van Hoff's factors. That's that I in the less simplified form right here. And the reason we add that in there is because if we're talking about adding solutes that have ionic characteristics like sodium chloride, if you have 1 mole of sodium chloride, that's going to dissociate into technically almost basically 2 moles of ions in solution. So you have the mole of sodium, the mole of chlorine. And so we take that into account, okay? It's going to be the moles of particles in solution over the moles of the formula units that are dissolved, okay? And that gives us this Van Hoff factor. So sodium chloride, for instance, it's going to be a Van Hoff factor of 2. Based on these, again, the moles that they dissociate into. Now, if we measure it, it's technically 1.9, but we use 2 because that's pretty close. Okay. So here's a problem that's asking, what is the freezing point, or no, the freezing point of aqueous 0.050 molality calcium chloride solution is negative 0.27 C. Okay. What is the Van Hoff factor for calcium chloride at this concentration? And how does it compare to the expected value? Okay. So for this, I don't have the calcium chloride expected value here. But let's do a calculation and then we can talk about how to figure out the expected value of that based on what we know about some of these other ones, okay? For instance, magnesium chloride, what's that expected value? It's 3, okay?
So pause, work on this, set it up with this relationship now, I, KF, molality, and see what you come up with. Okay. So again, our equation is change in temperature for freezing point is equal to the Van Hoff factor times the freezing point constant for that particular solution and the molality. Okay. Now this is for calcium chloride, right? We were looking for I. So we can get I by itself by just rearranging these and saying I is equal to the change in temperature over constant times molality. Now it didn't give you the constant in here, so you have to look it up, or I'll just tell you that it's 1.86 Celsius over molality. And the temperature, they said it was negative 0.27. So that change overall is going to be 0.27 as our delta TF. So 0.27 divided by 0.050 as the molality value that they gave us, times the KF. And if we, where's my calculator? If we do all this, divide it out, we get I equals 2.9. Okay. So it's asking us what is the I and how does it compare to the expected value? Well, what is the expected value? I guess that's the question. We said that sodium chloride has an expected value of 2, right? Because 1 mole of this goes into form a mole of sodium chloride, a mole of sodium and 1 mole of chlorine, and 1 plus 1 is 2. What's calcium chloride going to do? Well, that would go into a mole of calcium, a mole of chlorine, and then another mole of chlorine, because there are two chlorine atoms on that molecule. So our expected is 1, 2, 3. So our expected Van Hoff is 3, pretty close at 2.9. Okay. I think that what I'm going to do now is there's a few more freezing point depression. I'm going to take a pause here and post this lecture as a part 1. And then I will record part 2 as soon as I can and get that up, but that you guys can start watching this one. Part 2 is going to go into osmotic pressure. That's the last colligative property I want to cover. Maybe if I have some more time, I'll go over some of the problems that we skipped over in the slide deck. Okay, so see you next time.